Hey everyone! Thanks for joining us for the next session of our Python and AI Level Up series on vector embeddings. My name is Anna. I'll be your producer for this session. I'm an event planner for Reactor, joining you from Redmond, Washington. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenter and moderators to answer. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our speaker for today. Pamela, thanks for joining.
Hello, everyone. Very excited to be here for the second session in our Python plus AI series, where we show you all the fundamentals of generative AI with a focus of using them in Python. So we are on our second session where we're talking about vector embeddings. We already talked about the basics of LLMs. If you missed that one, you can go back on YouTube and you can watch that when you've got time. And we still have 7 more sessions after this one. So we're covering lots of topics in this series. If you haven't yet registered for the series, go and register for it now with that link that we'll post in the chat because we want to hopefully see you at all the sessions. Now, they will all be recorded, all the slides and all the code, everything will be available. So if you do miss anything, you can always catch up. So let's go to today's topic about vector embeddings. It's a really fun topic. It also is a little bit more of a mathy topic. So those, going to be a little more math today than other ones, a little more math than Python, but our goal is so that you walk away from this and really feel like you have a better intuitive understanding of vector embeddings, how they work, and when you might want to use them. So we're going to be talking about what they actually are, what the kind of similarity spaces look like for embeddings, how you search for them, how you can compress them with different quantization techniques, and we'll see that across a couple different embedding models. Now, you can follow along with everything I'm doing with this repo here, aka.ms/vector-embedding-demos. So we'll go ahead and post that in the chat. And that is a public GitHub repo. So you can go to the repo, and then the easiest way to get started is to click on the code button and go to the code spaces tab. And you can see I actually already have 2 code spaces. But when you click on it, what you should see is a giant button that says create code space on main. This button here. So you're going to click on that, and it will create a code space in your browser. So it's going to look like a VS Code inside your browser that is inside the actual project. So you can see I've got a code space open over here that has this project open. So that's what it'll look like when you open it. Is that you give it a couple minutes, it'll open this VS Code, and then you'll have access to all of these notebooks. And you should be able to run all of the notebooks that I'm running for free because we're using GitHub models for the vector embedding models, and that you can run for free using a GitHub account. So hopefully you can follow along with everything I'm doing if you want to by opening this repo in GitHub Codespaces. If you really want, you can also open it locally, but then you will have to do a little more setup and you will have to read the README. So if you do want to open it locally, go for it, but do check out the README to get some tips for setting up, and ask questions in the chat if you have any. Okay. All right. So we want to make sure everyone knows how they can follow along. And you can always open that repo later if you just want to watch for now and don't want to play around with the code yet. So now let's talk about what are vector embeddings. So at a very high level, humans think in words, right? And computers think in numbers, or really computers think in binary and bits. So if we're trying to get computers to be able to think about human concepts like words, we need to find a way of converting those words into something a computer understands. So what we do is we create these vectors that represent words and phrases and sentences. And they try to represent the meaning of those sentences, but in a numerical form. So a vector embedding is actually a list of floating point numbers. That is what it is to the computer. And that's something that a computer can actually use when it's doing, calculations. So when everything is in a vector form, it can do, ranking and sorting and searching. And so it is a way of capturing the meaning of human concepts in a numerical form that computers can understand. So that's what they are at a really high level. We're going to go much, much deeper into this, right? But they are lists of numbers that represent, words, phrases, sentences, inputs, concepts. And we've just figured out a way to turn it into something that a computer understands. Now, why do we actually need vector embeddings? Like, what are they useful? Why are you even here? So they're actually incredibly, incredibly useful. Once we have vector embeddings, like first, we can just make much better searches. So anywhere where you have a search, right? If you've got a product store that has a search, you've got documentation that has a search, anywhere where you have a search, you're going to improve that search if you add in vectors, vector embeddings and vector search to it. Now, on top of that, we can start building more interesting things and actually building chat-based interfaces for users, because we can take really, really ambiguous input from users, and we can handle any sort of input now. So we can take a user's entire question and we can use that to do a search, and then we can hand those results to an LLM. So many people that are building chat-based interfaces with LLMs are actually using vector search behind the scenes in order to handle these, more ambiguous queries from users. Once we start adding vector search, we can also, we can improve things because we can find things that are similar in meaning. We can also handle multiple languages more easily. So it's because a lot of these vector models actually understand multiple languages. So suddenly our search can understand multiple languages. We also have vector embedding models that understand images. So now our search can understand images. So just really, really can improve search across the board. So that's the big use case for vector embeddings. We are going to see a few other use cases as well. But there's just, there's so many great places where you can use vector embeddings in order to enhance the retrieval in software. Okay, so that was at a high level. So now let's start digging in. So how do we generate embeddings? We need to use a vector embedding model. So a vector embedding model is a special type of model that is trained specifically to be able to convert inputs into a vector. These days, it does use architectures similar to large language models, but it's not the same as a large language model, right? So it can use a really similar architecture like the transformer, but it has the goal of creating vector embeddings, of learning the similarities and differences between different inputs. That is its goal when it's being trained. And that means that it, creates an embedding model that specifically is really good at understanding which things are similar and which things are different. And these embedding models these days are trained on huge data sets, typically like from the whole internet, right? And they're looking at across the whole internet, like similarities and differences between words. So a vector embedding model can take an input and then output a vector, and it can do that for things it's seen. And then once it's been trained, it can do that for things it hasn't seen as well. And that's what, makes it really, really powerful. Now, there are different vector embedding models out there. The one that you may have heard of that we've had for many years is called Word2Vec, and that one is just knows how to turn a single word into a vector embedding, and that's one that you can even just run on your laptop if you want to train your own word-to-vec model. Very easy to make a word-to-vec model and be able to encode words. But the thing is that only encodes a single word at a time. Now, these days, we have vector embedding models that can encode really, really big inputs. And so the new like OpenAI embedding models, they can encode up to 8,200 tokens, which is huge. That's like a large amount of text, right? So you could take an entire essay and be like, hey, make a vector embedding that represents this whole essay. So these models are much more powerful because they can accept such longer inputs, and they can come up with a vector embedding that represents this really, really long input. And once we had these new models that could encode much bigger inputs, then that's when vector embeddings really took off, where people are like, whoa, like now we can, we can take any user input and we can just represent that as a vector embedding and just do so much with it. And the interesting thing with these models is that they output vectors of different lengths, right? So remember, a vector is a list of numbers. And so, like word-to-vec, typically that's a list of 300 numbers. OpenAI text embedding 80002, that was their first model, and that's a list of 1536 models. Now OpenAI has two new models, the text embedding 3 small and text embedding 3 large. And the 3 small is a vector length 1536, and then 3 large is a vector length of 3072. And then we also have the Azure AI Vision model. That one can take image or text. That's a multimodal embedding model, and we'll talk about that in the Vision series. That one has a vector length of 1024. So you can see there's differences in what kind of input they can take, how long their vectors are. And then there's also differences, in quality. So we have a leaderboard here. Hugging Face has this leaderboard to compare embedding models. So if you're curious to see the benchmarks for embedding models, like if a new embedding model comes out, then you can check out their embedding benchmark leaderboard and see how these models are doing. But generally what you see is like currently the OpenAI text embedding 3 large model is a really, really good model, ranking higher than any of the other previous OpenAI ones. So that's the one that I tend to use whenever I'm developing applications, because it does have the highest quality. So if you go here, this is the leaderboard, and this will show the rankings of the models here. And we can see, so I haven't visited in a while, but you can see that there's some new models here. So there's ones from Gemini, Qwen, and they look at different statistics here. So, and they kind of average and see which ones are the best. So you can dig more into that if you're interested in the benchmarks, especially if you're looking for embedding models to work for a specific language. They do have some benchmarks for different languages too, which is nice. All right, so now let's go ahead and generate some embeddings. So we're going to be focusing on the OpenAI models, since we can use those with OpenAI.com or Azure or GitHub models. And so in this case, I'm using GitHub models since I can use that for free. And we can create some embeddings. So I'm going to go to the actual code space to do this. All right, so I'm going to open up Generate Embedding notebook. So the first thing I need to do is create, I'm going to use the OpenAI Python package and connect to GitHub models. So this is the URL for GitHub models, and this is my key is my GitHub token, which is in the GitHub code space already. And I'm going to use the text embedding 3 small model here, which has 1536 dimensions. Now, next, I'm going to go down here, and then I can use that OpenAI client to create a new embedding. So I say, okay, this is the model I want to use. This is the dimensions, and then here is the input. So I can run this, and it goes off and creates an output, and you can see it's 1536, and we can see a bunch of numbers, right? So we can do, a different thing here, big dog. We could do in different languages, un perro grande. So, and we can do gobbledygook. I mean, that's the interesting thing is that you can turn, with these models, you can turn any input into a vector and it will try to represent that vector. But you can even put gobbledygook in there and it'll turn into a vector. And that, vector exists in this like multi-dimensional space, right? And so there, this vector lives somewhere inside this vector embedding space and is closer to some vectors and other vectors, even though this is absolute nonsense. So that's something to keep in mind with vector embeddings, is that, garbage in, garbage out. Like if you put in nonsense, it will give you a vector and at least pretend that it has some meaning. Even if it really doesn't have any meaning at all, but it wants to try and come up with some sort of representation of it, even though it has so little meaning, right? Now, most of the time we want to use this with things that, actually have meaning. So we'll, pass in actual phrases. Okay, so now we've seen that's how we can generate embeddings. And I have a bunch of embeddings already pre-computed in this workspace, so that we'll be able to look at a bunch of different vectors of different inputs without having to wait for it to do lots of embedding generation, because it does take time to generate the embeddings. The model dimensions. So this model dimensions, let me just change this. This is 1536, and this is text embedding 3 small. The model dimension does depend on the model. So you would need to check and see, for a particular model, what dimensions it supports. We will see later that OpenAI does actually support doing smaller than the default for some of their models. And that's an option. But by default, this model is 1536. And so that's what we're specifying here. Generally, like embedding models, they all have their own similarity space. So we need to know when we create embeddings, which model we used and how many dimensions we used, because whenever we're going to use those embeddings going forward, we need to use the exact same model and the exact same dimensions. All right, so now let's talk about, different models, right? So I was just saying, like, it's really important that we know which model we're using, because every embedding model has its own similarity space. It's like its own brain, and some brains have different similarity spaces than others, right? Like in my brain, like there's a different similarity between like unicorns and ponies than in somebody else's brain. So what we need to do is know which model we're using and stick with it, so that we're able to actually compare things. So here's a comparison between the two OpenAI models, right? Looking at 2 different vectors. So for the same word, I can pass the same word queen into their older model, Eta002, and we do get a vector of 1536 dimensions. But it's kind of a weird, vector. If you look at it, most of the values are really, really close to 0. But then there's this value here that is like negative 0.7, right? And this is the weird thing about this model, is that every single vector has a value at negative 0.7 in the, it's dimension 196, always has a value that goes really, really low like this. So it's a weird thing about this vector embedding model, that this is what the numbers tend to look like, is that they're mostly around 0, 0, and they have a couple super downward spikes, right? And I saw that with every single input that I put into this model, that it all had this really similar spike downward here. Now, the text embedding 3 small model also outputs 1536, but the actual values look much better distributed, right? So here we can see the values of these numbers range between 0.1 and negative 0.1. And, they're just kind of all well distributed over that, right? There's no like really extreme spikes like this one. So, to me, this means I think this is a better model. I think they did a better job training it, that they don't have any weird artifacts like this one. Now, the thing is, when you look at this, what does this even mean, right? Like, you can't look at a vector and see the meaning in it, right? You can only like really understand how a similarity space works when you then compare and see, like, what does it think is similar, right? That's how you can understand a vector similarity space, is by seeing what does it think is similar to other things. So let me look, let me open up another notebook here, right? So we've got embeddings for a bunch of words across a few different models. So like Ada 002 and text embedding 3, right? And what we can do is, oh, actually what I want to do is look at, wait, which ones are similar? All right, so now let's talk about similarity, right? So as I was saying, the way to really understand a vector similarity space is to see what it thinks is similar to each other. Now, how do we actually measure similarity? The most popular net metric, and the one we're going to use today, is cosine similarity. So let's see cosine similarity in the similarity notebook here. And I'll go ahead and load these up. All right, so I'm loading in the embeddings that I've already generated for 1,000 words across each of the models. Now here's the cosine similarity function. So cosine similarity is the dot product divided by the magnitude. So first we calculate the dot product, and then we calculate the magnitude, and we divide them. So here we've got that implemented. And so now we can measure the cosine similarity between dog and cat. And so we get this number 0.6. And in this case, 0.6 means, you know, they're fairly similar, right? Now here's what's interesting about cosine similarity. See how it's dot product and magnitude. Now the magnitude of a vector is 1 if it's a unit vector. So this is just, this, you know, I said we were going to do a little bit of math, right? So if you remember from vector class, a unit vector is a vector that has a magnitude of 1. So if you have unit vectors and you do dot product over magnitude, then you're really just doing dot product, right? So let me actually show you. Let's print out the magnitude here. Print the magnitude. We'll run this. And you can see the magnitude is basically 1, right? With a, you know, like a little margin of error here, but the magnitude is basically 1. And that's because the OpenAI embedding model vectors are unit vectors. So that means I can actually speed up my calculation here when I'm using OpenAI models, because I can delete magnitude and just do dot product. And remember this similarity 0.602. I'm going to run this. I'm going to run this. Boom. 0.602. So I just saved myself a whole calculation because there I only have to do the dot product. Now this only works if you're working with a model that produces unit vectors. So that's true of all the OpenAI models. So if you are using OpenAI models, you can actually save yourself some time by just using dot product and not dividing by the magnitude. And sometimes it doesn't matter because you're using, you know, a vector database, and the vector database, you know, just takes care of this for you and does the optimization. But sometimes it does matter. Like when I'm using Postgres gives you the option to do cosine similarity or dot product. And if I'm using the OpenAI embedding models, then I use the dot product metric instead. So I think it's worth knowing that there is a slight performance improvement that you can get if you know you're working with unit vectors. Okay, so that was our math for today. So now and we do have lots of resources for anybody who wants to dig deeper into the different distance metrics. It's some pretty interesting stuff. I do wish I'd paid more attention to vector math in college now. All right, so now that we have a way of calculating similarity, we're going to go ahead and look for the most similar words to a given word using that metric. So basically, we're going to calculate the similarity from one word to every single other word in my collection of words, because I've got 1,000 words. So I'm going to calculate and see like, okay, for the word dog, which of the 1,000 words is closest to it according to cosine similarity. So for dog, I can look here and see that, okay, the closest one is dog. Okay, so that's good. Dog to itself gets a similarity of 1. Very good. Now the next one is animal. So the very closest one after this is 0.88. So it has a cosine similarity of 0.88. Now the one after that is God. So according to this model, God is actually more similar to dog than cat. So I guess this model is like a dog person. This model really likes dogs. I know. I think the reason is because of the spelling. Generally, what I've seen is that this is the ADA002 model. I think the ADA002 model did kind of incorporate spelling during its training process in a ways. I'm not sure exactly why, but this is interesting to see, because you're like, if it thinks dog is close to God, how might that affect other ways that I, would use this model? And then we see also drug and gun at the bottom here, right? So I think once again, drug probably maybe close in terms of spelling, maybe. Also, this is only looking at 1,000 words, and maybe there weren't any more similar words here. But this is what I find useful, is that if you're trying to understand a similarity space, is to see, in that similarity space, what do they think is similar, to each of the inputs. Now we can look at the same, we'll look also at the text embedding 3 small model. So that one actually has much more reasonable, right? Here we've got dog, then we've got animal. Now what's interesting is that animal here has a similarity score of 0.68. And if you looked up here, the closest thing is 0.88. So this is another thing you'll notice, is that you shouldn't think of similarity scores as being absolute, right? Because they differ so much across models. Like, so in the ADA002 model, 0.88 meant very similar, right? But in this model, 0.68 means very similar. So you cannot look at a similarity score on its own and know, oh, that's like a really, really similar thing. You can only look at it relative to similarity scores from the same model, right? So here we're seeing like, okay, so for this model, 0.68 is, a close score. We see animal, and then we see horror. So cat is 0.60, and that to it is actually a strong similarity. And then we go, all the way down to baby and door. I guess dogs are at the door a lot, so that might be why it thought it was similar. Because a lot of times when these models are trained, they're trained by looking at proximity in text. So if dog is close to door in a lot of text, then that can increase the similarity score, right? Maybe dogs are hanging out with the babies, like Lady and the Tramp, they're taking care of them, right? Who knows? But I'd say this is a much more reasonable set of similar words than ADA002. That's why I have moved everything over to the new models, because I think they just have a more reasonable similarity space. All right. Cool. So that I think is a really helpful way of understanding a model. Now you can also try to visualize the model. So here I used this technique called PCA, Principal Components Analysis, and it tries to turn the 1,536 dimensions into just 3 dimensions, so we can plot it in 3D space. And it's fun to do this, and it's cute, and it makes cool visualizations, but you lose so much information because you're literally losing 1,533 dimensions of information when we try to squeeze them down into 3-dimensional space. So, it's fun to make these 3D projections of the vectors, but I don't actually think it's that useful because we lose so much information. So I think it's more useful to actually just say like, okay, for a given word, which concepts are the most similar. But we like to see pretty graphs. So here you go. Here's some pretty graphs. Now, another thing that's useful is looking at the actual values of the cosine similarity, right? So we were looking, I was showing like, okay, so here, we saw the closest one was 0.68, and then here the closest one was 0.88. So I think that's useful to look at to give you a kind of more better intuition for a particular model, what kind of values to expect. So for eta002, all of the values are between 0.86 and like 0.78, right? They're in a really, really tight range. Versus the newer models, text embedding 3 small, we see the values range between like 0.7 and 0.05. Like that's a much more reasonable range. That's another reason why I think this is a better model, because it just has a better distribution across the range. And this one, you could actually look at the values and be like, okay, if you get a 0.2 cosine similarity, probably means not particularly similar, right? So it's easier to come up with the kind of cutoffs to say like, okay, if it's below this, similarity value, it's just really not that similar at all, right? So I think it's interesting to look at the range of similarity values to get a feel for what you might expect. So now we have seen cosine similarity, vector similarity. I see there's lots of discussion in the chat about the math behind it. So definitely you can dig into that more. Now there's some great use cases for just vector similarity on its own. So you can use it to make recommendation systems. In the past, if you wanted to make a recommendation system, you'd often have to look at like lots of user input and consider what different users liked and say like, okay, if lots of users liked this, then and they also like this, like, okay, those are similar, we're going to recommend them. That's still a really great thing to do if you can build a whole user-based recommendation system. But you could also now just use vector embeddings for making recommendation systems, and it's a lot easier. Because these vector embedding models have been trained on the internet, so they have a rough idea of like which things are similar. So I know people who have use this just to add like recommendations onto their personal blog or something, right? Like, so now it's so easy to make recommendations that you can do it for anything. You can just throw it on there right now. You don't have to build your own recommendation model. You could just use the embedding models, and then boom, you can show, hey, you're on this piece of content. Let's recommend these other content based off of what you're currently on. So that's definitely a big use case that you can consider for using vector embeddings. Great way to get started with it. Another interesting use case is fraud detection. So people use vectors in order to establish whether a new input is more similar to a fraudulent input than a real input. Now, this you really need to do very carefully because you don't want to accuse anything of being fraud if it's not fraud. Similarly, like spam detection. So that would be another use case for vectors. Now, interestingly, when people are doing fraud detection, sometimes they use different metrics other than cosine similarity. So here today, we're really talking a lot about cosine similarity because that's the metric that people are using for most of the generative AI use cases that we're looking at. But for fraud detection, sometimes people use other distance metrics as well. So cosine similarity is a great metric. It's the one we're showing today because it's going to be the most useful for all your generative AI applications. But just so you know, there are other ways of measuring the distance between vectors. And, sometimes other metrics are more appropriate for the scenario, like with fraud detection. Okay, so now we can talk about how we can do vector search. And that's really what everybody's so excited about in terms of vector embeddings. So the idea is that once we have all of our data converted into vectors, we can then search that data based off any new user input, right? So we get in the user input, we turn that into a vector using the same model, and then we use that vector to search existing vectors and say, okay, based off that new user input, here are the closest vectors that we have. So we can start off by doing an exhaustive search. So an exhaustive search means that we are going to take the input vector and we are going to use that input vector and compare its cosine similarity to every single other vector and say, okay, we found the vector that is closest to this input. So let's see, let's look at search, the search notebook here. And let me run this. So here, I've got a bunch of embeddings for Disney movie titles. Let me actually show you what those embeddings look like. Text embedding 3, movies, text embedding 3, small, 1536. Okay, let's see if I can get it to open the file. It is a really, really big file. Generally, you don't want to store embeddings in JSON files. I did it for this notebook because I didn't have that many, but they do take up a lot of space. So here I've got a bunch of embeddings for Disney movie titles. So I took the movie title and then I generated the embedding. So solely based off the title, that's how I generated the embedding. So that's what I'm loading in here. So I've loaded all of those in. And then I'm going to set up my connection to GitHub Models. And then I'm going to make a little wrapper function that can generate an embedding using the OpenAI SDK. And then I've got my code here to compute cosine similarity and do exhaustive search. Now, I was saying we could actually just remove the magnitude calculation since we know they're unit vectors, but we can also just leave it in because that's the standard way of doing cosine similarity. And so then we're going to create a new vector, right? So here I've got the input, a toddler-friendly movie about cats, right? I have 2 daughters and they often want to watch a movie about cats. And we have Disney Plus, right? So here I'm trying to search for what is a good movie that we could watch that they would like. So we get the embedding for that input. Then we use that embedding to search all of our existing vectors. So we say, all right, let's calculate the cosine similarity. Let's get them all and let's sort it. So let's see what we get as a result. Okay, so the top movie is the Aristocats. Then we have the Tigger movie, then Ratatouille, then Cars 2. African Cats is somewhere in here. We have the Goofy movie. We've got dog movies. Unfortunately, there's actually not that many movies about cats on Disney Plus. It's unfortunate. But this is a pretty good result here. Now we can put in all kinds of things, right? So we can do something in Spanish. We can say like, okay, películas sobre leones, which is movies about lions. And here we get the Lion King, right? So it's saying like, once you're using vector search, you're able to support so many more searches, right? Like, and we can be like, really, really like, oh man, my daughters are screaming for unicorn stuff. I need to occupy them right now, right? Like this is just a stream of conscious input from a user, but a vector embedding model can turn anything into a vector. And here we can see the result it suggested was Babes in Toyland. Actually, I haven't watched that one yet. And then Monsters, Inc., Ice Princess, right? So these are like, they were like, okay responses. I guess there's no unicorns actually in this data set. Let's see, kitty, dinosaur. Well, let's try dinosaur. Do we have any dinosaurs results here? Dinosaur, there we go, right? So I had this whole long stream of consciousness and it picked out that, dinosaur was a salient, part of that vector, right? And so, it's turned this whole phrase into a vector that lives somewhere in that multidimensional space. And fortunately, that vector is closer to the dinosaur vector than it is to any of the other vectors, right? So that's what's really powerful about vectors. Okay. So there we go. So that's pretty cool. Now, I saw a comment in the chat that exhaustive search sounds expensive, and that's true. right? So here we're only searching, what is it, like 500 movies, something like that. And so we're able to do the exhaustive search, and the exhaustive search is, relatively fast. But when you're actually using vectors in production, you're going to have much bigger databases, right? You're going to have thousands of vectors, millions of vectors. You could even have billions of vectors. We do actually have customers at Azure that have billions of vectors in their database. So what we can do here is then use approximation searches. So we need to use an algorithm known as an approximate nearest neighbor search, so ANN. So these are all search algorithms that try to find the best result without actually having to search exhaustively, right? So they're trying to find the highest quality result without having to look at every possible option. So they have to use some sort of heuristics to cut down the search space. Now, the most popular one these days is HNSW, and that has really good support across lots of databases. So Postgres supports it with the PG vector extension. Azure AI Search supports it. ChromaDB, WeVA, pretty much all the big vector databases are supporting HNSW. And so that's a great pick. So if you see that as an option, that's a great pick. Now, Microsoft came up with a new approximation algorithm called DiskANN. And so we're now using that for several Azure products. So Cosmos DB has it, Azure SQL has it, and Azure Postgres has it. So if you're using Azure Postgres, you can actually pick between HNSW or DiskANN. There's also IVF flat, and that is supported by Postgres. It's not as supported by the other ones because it's not quite as practically useful for a lot of production uses of vectors. It's got some limitations. Like IVF flat works best if you're only going to make the vector index once and you're not doing lots of updates. But a lot of times if you have a database, it's because you're going to be updating that database, right? So you want something that works well, that can handle lots of data updates. And then there's FICE. FICE is something you could use if you just needed an in-memory index, but it's not designed for, like a persistent database. So we're going to look at HNSW because it is, the most popular one that a lot of people are using, and you can use it just in Python. So I wanted to find an example that we could run in Python without having to set up a database today, just so you could get a feel for it. So HNSW does work well in situations where you have an index that's frequently updated, and it can scale really well up to large indexes as well. So it's a very well-designed algorithm, and we can use it for a lot of our production use cases. So I actually have that set up in the notebook here using the HNSW lib package. So we, declare our index, we say how many dimensions it's going to have, and that we're going to use cosine. And we have some parameters here that you can tweak in order to change stuff like the performance of the index. And then we can add all the items to the index. And then and basically at this point, the index is set up. Now, usually you're not going to be the one writing all this code. Typically, you're going to use a database like Postgres that's going to set this up for you behind the scenes, maybe with some database commands. But I thought it was helpful to see that you can do it in Python. So now I can get my embedding for the toddler-friendly movie. We'll say about dogs, since it seems like there's some dog people in the chat. And we're going to get that embedding, and then we're going to do a query. So this is a KNN query, which says get us the 10 closest nearest neighbors, the 10 nearest neighbors based to this vector. And then we display them. All right, so we got lots of dog movies, right? So that was fast, and it did a good job. So the idea of HNSW is it should get you really similar results to if you were doing exhaustive search. Like, let's go try the same thing up here, a toddler-friendly movie about dogs. All right, we'll run that. Snow dogs, 102 Dalmatians, fox and hound, right? And what we see is basically the same results down here. And of course, this was on a really small index, so we would expect to see really good results. But the idea of HNSW is that even as you're adding more and more vectors, you can keep getting really, really high quality results. And so not having to sacrifice the quality, but still get really good speed. All right, so that was vector search. So what are the use cases for vector search? Like, first of all, if you have any sort of search box on your web app, on your website, you can enhance that search box by adding in vector search, because then once you add in vector search, you can handle more complex queries, more ambiguous queries, right? You can handle multilingual queries, right? So it can generally just improve any sort of search that already exists. And then the really big use case with LLMs is RAG, is where we're using an LLM to answer questions by searching some data. And we're going to be talking about that really in depth tomorrow. So please, come to tomorrow's session where we're going to be talking about RAG. But this is really where vector search has taken off, because when people talk with LLMs, they don't use search queries to talk with LLMs. They ask questions, right? So we need to be able to take questions from users and be able to use those to do vector searches, right? So I have, so for example, this is a RAG on top of Azure AI Search that's searching documents like PDFs, right? So this one is doing a vector search of documents, and we can actually see the kind of scores that come back from the search service for the various chunks, right? So we have created embeddings of all of these chunks from the documents, and we are searching based off of the embeddings of these chunks. And that way we can get really good results, and then send those results to the LM and get a good response. So that is RAG, and that is what we're going to be talking about for the whole session tomorrow. All right, so now moving on, let's talk about how we can compress vector embeddings. So as you see, our vectors, vectors take up a lot of space, right? Like this is, the title of the movie, and the actual vector is really, really, really long. And this is actually the small embedding model, right? This is 1536. Usually I use the large model, and that's 3072, right? So, once we start using vectors, we are increasing the amount of storage space that we need for our data, and then we're actually paying for that storage space, and it affects how well we can productionize the applications that we're building. So when you are thinking about putting your vector search into production, you may think about how you can compress the vectors to decrease your storage size and cost, and also decrease the search latency. And as it turns out, there's two really interesting techniques we can use to compress vectors and not lose that much quality. So we're going to look at vector quantization, where we take each number and we make them take up less space. And then also dimensionality reduction, where we just take a long vector and make that vector shorter. So let's talk about vector quantization. So this is where we start off with the list of floating point numbers, right? That's what we just saw, tons and tons of floating point numbers. These are 64-bit floating point numbers. And so they require a full 64 bits in order to store in memory. But what we can do is reduce them so that they don't require 64 bits. We can start off with scalar quantization. That's where we reduce each number to an integer. And then we can even go as far as binary quantization, where we reduce each number to a single bit. And it's crazy that that works. So let me go ahead and open the quantization notebook here. And here we have, okay, so we're going to load in the same ones from before, the 1536. All right, so we can see these are currently 64-bit numbers. Now, for scalar quantization, the approach that we use is that we have, we look and see, okay, what is what is the range of these values? What do these floating point numbers range between? And what's kind of the middle of those values, and we take the range of those values and we map them to the new range. So for this code here, I'm going to map the values from -128 to +127, right? So it's going to take all those floating point values, and each of them is going to fall into one of 256 buckets between this range. So you can see here, we find the global min and max. We normalize the embeddings. And then we go and figure out, okay, between the min and the max, where is, which number is it going to become? So go ahead, I can run this on the Little Mermaid. And now we can see that the Little Mermaid is represented by a list of integers instead. And integers require much less storage space than 64-bit, floating numbers up here. So now we've got that that vector. You can look at it and see that once we've mapped it into integers, all of the values range between. In this case, we can see they went from like -10 to +70 for this vector. The full possible range is -127 to +128, but it just depends where the values fall. So now what the big question is, like, okay, well, we removed a bunch of information, right? We went from 64 bits of information to just an integer of information. How does that affect similarity? That's what matters, is are we going to get the same results? Like I saw a question like, are we getting the same results with H and SW, right? That's always the question. Like as you add on approximation and compression and all of that, how good are the results, right? A lot of times they're not going to be as good, but a lot of times they could be good enough, right? So here we can look and see like, okay, Moana, with the integers, we see the most similar values, similar movies are like Mulan, Little Mermaid, Lilo and Stitch. And we can compare that to the original, where we see Mulan, Lilo and Stitch, Little Mermaid. So like the top three, they're in a slightly different order. I'm going to try and show it all. So here they're in a slightly different order, but they're pretty darn close, right? So given how much performance improvement we can get out of this, this might be good enough, right? But it's something you really have to decide and actually run evaluations and see like, okay, like once we like add in this performance enhancements, we add in this quantization, is our performance still good enough? Like, is our retrieval quality still good enough? So the next thing is we can go more extreme, and then we can turn each of the numbers into bits, just 0 or 1. And so for this one, what we do is we look at the full range and we figure out the average, like the mean, the one in the value in the middle. And if it's less than that, it becomes 0. And if it's more than that, it becomes 1, right? So that's what this code here does, figures out the mean and then quantizes to either 1 or 0. And so then we can see Moana becomes, 1101001, right? And it's crazy to think that this, that we could do this. Like we're losing so much information. We went from 64 bits to 1 bit. And I was actually working on this notebook with my mom, and my mom, she's a mathematician, and she did not think it was going to work. She was like, no way, like we're going to lose so much data, but let's just look and see. All right, so that's what the vector looks like. So here, when we look at the most similar movies, we see Moana, Mulan, Little Mermaid, Princess and the Frog did move up 1, but then we got Lilo and Stitch here. So we still seen really similar results, even with 1 bit to represent that full 64-bit floating number. So that's what's really, really interesting, is that you can actually reduce so much information and still retain a lot of the semantic meaning in that vector. Oh, and I see there's a comment about like, oh, the similarity numbers are different. That's true. The similarity numbers are different. That's why they're saying like, it's important that we, usually we don't want to strictly be looking at similarity numbers on their own, and we want to look more relative, right? So relatively, we see that within this search, Mulan is more similar than Little Mermaid, but it's true that this one's 0.68 and this one is 0.54, right? So really different similarity ranges here. So if you were doing any sort of similarity threshold cutoff, it does really depend on, in this case, it would depend both on the model and the space and what sort of quantization you were doing. So that's a good observation there. Okay, so that's crazy, but it worked, right? And here I've got the actual effects on similarity between the float and the binary. Like there's definitely differences here, and we can argue about which of the results are actually better. But it still did retain a surprising amount of semantic information because it did come up. It wasn't just nonsense, right? Like it came up with a bunch of similar movies, just some differences in which is which. Now, the cool thing is for if you're, just working a few thousand vectors, it's not a big deal. But if you are doing millions of vectors, billions of vectors, like this can make a big difference in reducing the size of your vector index. So here we have a comparison for Azure AI Search, which supports quantization. And so if we start off, with float 32, and then we go down to bits, we can see that we get a 97% reduction in the index size. So that's huge, right? Because that's money that you're actually paying for. And, if you don't need to use up all that space, then, why use it? So that's quantization. And now let's look at the other technique, which is dimension reduction. So dimension reduction is a technique we can only use on models that were specifically trained to be able to support it. So the OpenAI embedding models were trained to support MRL, Matryoshka representation learning. So since they were trained to support MRL, it means that we can reduce those models to different sizes and still retain a lot of the same semantic representation. But you do have to be really careful to only use this on the models that support it. Now, the cool thing is with the OpenAI SDK, you can actually just do it in the SDK itself. So, when you're using the model, just pass in the smaller dimension. So for this one, 3 small is usually 1536. I can just pass in 256 and it will do the correct reduction and give back the new embedding. So does this work, right? So I did the same comparison here. So I went from 1536 down to 256. That's the minimum that that is supported for reduction on this model. And what we see is really similar results with some differences, right? Similar to quantization effects. So the interesting thing is you can combine these techniques. So you could take start off with 1536, reduce those to 256, and you could then even in theory reduce those 256 things to only be bits instead of floating point numbers, and you would have this index that takes up this tiny amount of room. But I know you're probably all freaking out oh my God, you're definitely going to lose some quality with that, right? You're definitely, because you're losing information. You're losing information in all directions, all dimensions, right? But there's this really cool hack or technique that you can use, which is to oversample, right? So what you can do is let's say originally you wanted 10 results and you were going to do those 10 results on your, non-compressed index. What you can do is say okay, I'm going to get 150 results. And I'm going to ask for 150 results from my compressed index, and then you can still store the original vectors in a more efficient place to store vectors, not in your actual index, but in a different spot. And then you can rescore the results according to your original vectors. And so basically, if you ask for 150 results, you're going to find that those 150 results are going to have the original top 10 best results. So you get those 150, you then rescore the 150 using the original vectors that are stored elsewhere. And then you'll find those top 10. The top 10 will rise out of that, right? So that's it. I mean, this is getting to use cases that maybe not everybody needs, like maybe you don't all need these compression, but we do work with lots of customers that do have lots and lots of vectors. And this is what we recommend is like, okay, use all these compression techniques, but then use what we call oversampling, right? So use oversampling with the original vectors in order to rescore. So I think it's really, really a cool technique, and that we can use in order to have fast retrieval from the vector index, but still have high quality results. We did like a whole series about it where we did a deeper dive into it, and I was really impressed to see the results. Is if you can do all of this, and as long as you do the oversampling with rescoring the originals, you get fantastic results. Okay, so we covered a lot today. As I mentioned, we did go kind of deeper, nerdier into the math of it, because vector embeddings, like, they're a bunch of numbers. Like we have to think about what they actually mean and how we, compute distances and all that stuff. Hopefully this gave you a better feel for vector embeddings. If you have any feedback about how to make them easier to understand, let us know. There's lots more resources here that I used when I was researching vector embeddings, and you can get these resources from the slides, and you can dig deeper into it. I also have, let me find my blog post. So I have this blog post here that is kind of like a written version of this one. And I actually even turned this into a poster. So if you like posters, you can have a poster of all these. This mentions a few other things like the other distance metrics. So this was one way of exploring the amazing world of vector embeddings. And we will keep using vector embeddings going forward in the series, especially tomorrow. So please come to the RAG session where we're actually going to do practical things with vector embeddings and see how we can use it for making RAG applications, which is the most popular use of vector embeddings. We will also revisit vector embeddings in the vision models on Monday. So we'll get to see multimodal embeddings, which are really, really cool because you can search by image and you can search images. And so that's really, really helpful. So we will continue to talk about cool ways of using vector embeddings going forward in the series. So I hope you come back, and I hope that we get to see you tomorrow. Let's see. We do have office hours on Tuesdays. We already had them yesterday. It was a great office hours. Lots of you came and we had lots of great questions. I don't have office hours today, but you can still join the Discord, and there's lots of channels in the Discord where you can ask questions. Another place you can ask questions is on our resources thread. So we're keeping all the resources in this discussion thread here. So if you do have any additional questions, please feel free to add them to this thread, and I can totally answer follow-up questions there. And let's see what else. We are at time right now, so we can't go over today with questions, but hopefully you got a lot of questions answered in the chat, and please do post any more questions in this thread or in Discord, or bring it to office hours next week. All right. Thank you, everyone. I hope to see you tomorrow. Bye.
Thank you all for joining, and thanks again to our speakers. This session is part of a series. To register for future shows and watch past episodes on demand, you can follow the link on the screen or in the chat. We're always looking to improve our sessions and your experience. If you have any feedback for us, we would love to hear what you have to say. You can find that link on the screen or in the chat. And we'll see you at the next one.